Now we discuss a physical property of a class of insulating materials called ferroelectricity. Materials that can be polarized under certain temperature or in a certain range of temperature without the presence of an external electric field are known as ferroelectric materials. Such materials exhibiting spontaneous electric polarization include Rochelle salt or potassium sodium tartrate, barium titanate, and potassium niobate. The distinguishing properties of ferroelectric materials can be summarized as follows. Ferroelectric materials exhibit exceptionally high permittivity and their dielectric constants can be in the range from thousands to over 100,000, whereas the values of relative permittivity are typically below 10 for common dielectrics. In this table we compare the baseline values of the relative permittivity epsilon R of common dielectric materials from silicon dioxide to titanium dioxide with those of some ferroelectric materials starting with barium titanate. It can be seen that the permittivities of the former group remain in the range under 100. Whereas the lowest values of epsilon R is in the order of magnitude of thousands for the ferroelectric materials, and its baseline value is 80,000 for calcium copper titanate shown in the last line. In the third column of the table we display the Curie temperatures of the different ferroelectric materials which we will discuss later. In the case of ferroelectric materials the dependence of the polarization vector on the electric field strength is not linear. Unlike to the majority of dielectric materials, their relative permittivity and electric susceptibility are not constant but functions of the electric field strength. If we change the magnitude of the electric field strength, then the degree of polarization and hence the value of the electric displacement at a given moment in time is influenced not only by the instantaneous value of the field strength but also its previous values, that is the polarization and the electric displacement in a ferroelectric material depend on its history. This phenomenon is known as ferroelectric hysteresis. The plot describes the dependence of the magnitude of the electric polarization vector P of a ferroelectric material on the magnitude of the electric field strength E applied to the material. It shows the lat of the polarization behind the electric field forming a hysteresis loop in the P versus E diagram. The red curve in the plot depicts the behavior of ferroelectric materials when we increase the magnitude of the field strength from 0 at the origin O to the value EA, achieving a maximum value of polarization at the point A in the plot. PS is the saturation value of the polarization of the material at the point A. By reducing the magnitude of the field strength from EA to 0, we follow the blue curve where the value of the polarization decreases, but it does not vanish even if the electric field applied to the ferroelectric material vanishes. Instead, a finite remanent polarization PR remains in the material, indicating its ability to store stable memory states. A reverse electric field EC called coercive field is required to bring the polarization back to 0 at the point B on the blue curve, and only a further increase in the reverse field can achieve a saturation value of the polarization vector pointing in the opposite direction at the point C. If we decrease the reverse field applied to the material so that it vanishes and then increase in its initial direction again, then we obtain the yellow curve from between the points C and A. The hysteresis loop is formed by the blue and the yellow curves in the polarization versus field strength plot. The microscopic origin of ferroelectricity is related to the special crystal structure of ferroelectric materials. We already saw that in the molecular structure of a non-polar dielectric material the center of the positive charge of the nuclei coincides with the center of the negative charge of the electron cloud, producing electrically neutral atoms without an external field in the crystal. Ferroelectric materials are a specific subcategory of polar dielectrics, that is, they have a crystal structure in which the equilibrium positions of the ions are such that the centers of positive and negative charge do not coincide. As a result, ions behave like electric dipoles, producing spontaneous polarization even if no external electric field is applied to the material. In thermal equilibrium, the molecular orientations in common polar dielectrics are random, so the average polarization in the matter is 0. Under the influence of an external electric field, the electric dipole moments of the molecules tend to align in the direction of the field. When the field is removed, thermal motion randomizes the orientations of the dipoles again. Ferroelectric materials are different since a macroscopic crystal in them is usually not polarized uniformly, but it breaks into ferroelectric domains. In the absence of an electric field, the macroscopic material can be considered as a disordered set of domains with permanent polarization pointing in different directions, so that the net polarization may be small or even 0. The electric dipoles act cooperatively within a ferroelectric domain, whereas the orientation of each dipole is aligned individually by the external field in common polar dielectrics. We can illustrate the situation of the disordered set of domains at the point O in the polarization versus electric field strength diagram if we depict some of the domains in the ferroelectric material. We draw a red isosceles triangle inside each domain with its vertex pointing in the direction of the collective orientation of the dipoles inside the given domain. When an external electric field is applied, the dipole moments and the polarization vectors of the individual domains are arranged in the direction of the field, which is characterized by the red curve on the graph. Reaching the saturation polarization PS at the point A in the diagram, the entire macroscopic material can be considered as a single domain of a polarization pointing in the direction of the field. In this saturation state represented by the point A, the electric dipoles in all domains point in the direction of the external field. When the field is reduced back to zero along the blue curve, the polarization does not return to zero but the remanent polarization PR remains because many domains stay aligned. To reduce the polarization to zero, the coercive electric field EC in the opposite direction must be applied, producing completely disoriented domains in the material at the point B, as shown in the figure of the ferroelectric domains. By further increasing the reverse field, the dipole moments and the polarization vectors of the disordered domains can be arranged in the direction of the reverse field till they form a single domain at the saturation point C. If we decrease the reverse field to zero and increase the electric field in its original direction, we can reorient the domains the direction of the field again, moving from the point C to the point A along the yellow curve. The displacement vector D for ferroelectric materials can be written as the vector sum of the vacuum permittivity epsilon naught times the electric field strength E, and the polarization vector P, where the later depends on the field strength. Now we define the differential permittivity epsilon D by the derivative of the magnitude of the displacement D with respect to the magnitude of the field strength E. If we substitute the expression for the displacement into the derivative, the differential dielectric constant can be written as epsilon naught plus the derivative of the magnitude of the polarization P with respect to the magnitude of the field strength E. This result shows that the differential permittivity epsilon D of a ferroelectric material gives the tangent of its hysteresis loop at a given point, as indicated by its graph drawn for the yellow curve between the points A and C. Its maximum is at the point of inflection of the curve, and the differential permittivity drops from the maximum to the value of the vacuum permittivity as we approach the saturation range of the polarization. The differential relative permittivity epsilon sub RD of a ferroelectric material can also be defined such that its product with the vacuum permittivity epsilon naught is equal to the differential permittivity epsilon D of the material. That is, epsilon sub dr is just equal to the ratio of epsilon D to epsilon naught. Similarly, the differential susceptibility chi D of a ferroelectric material is given by 1 over the vacuum permittivity epsilon naught, times the derivative of the magnitude of the polarization P of the material with respect to the magnitude of the field strength E applied to the material. Then the differential relative permittivity epsilon sub RD is equal to 1 plus the differential susceptibility chi D, that is, they have the same relationship as the one between the relative permittivity and the electric susceptibility for standard dielectrics. As already mentioned, in the table where we have shown the relative permittivities of ferroelectric materials, their baseline values are used, that is, the initial slope of the displacement as a function of the electric field strength, determined by the tangent to the red curve at the point O in the polarization versus field strength diagram, where the electric field vanishes. In the table comparing the relative permittivities of common dielectrics with the baseline values of the dielectric constants for some ferroelectric materials, a critical temperature Tc called Curie temperature was also shown for ferroelectrics. In 1895, Pierre Curie first recognized the existence of a critical temperature above which ferromagnetism disappears, and this phenomenon was later extended to ferroelectricity. Above the Curie temperature, ferroelectric materials lose their spontaneous polarization and transition into a perielectric state, where they behave as standard dielectrics. Rochelle salt, the oldest known ferroelectric material, exhibits two Curie points, upper and lower critical temperatures at -18 Celsius and 24 Celsius, and only acts as a ferroelectric material within the temperature range between them. The Curie temperature of pure barium titanate, one of the frequently applied ferroelectric material, is typically around 120 degrees Celsius to 130 degrees Celsius as seen in the table. Calcium copper titanate shown in the last line of the table is an incipient ferroelectric material and has no classic Curie temperature, because its polarization does not originate from the crystal lattice itself, but from the accumulation of charges at interfaces inside the material. In a perielectric state above the Curie temperature, the centers of positive and negative charge coincide in the crystal and the spontaneous polarization of the material is zero. Then we cannot talk about any preferred direction for the polarization field in the material, that is, the ferroelectric crystal possesses inversion symmetry. Below the Curie temperature, the material is in a ferroelectric state where a slight displacement of ions in the crystal breaks this inversion symmetry, creating a non-zero spontaneous polarization which defines a preferred direction in the crystal. This phenomenon is considered as a ferroelectric phase transition in which the crystal changes both its symmetry and its electrical properties. The reduction in symmetry from the high-temperature disordered phase to the low-temperature ordered phase is the key idea of the theory of continuous phase transitions developed by Lev Landau in 1937. Because a thermodynamic system at constant temperature and volume reaches equilibrium by minimizing its free energy, Landau assumed that near the phase transition free energy can be expanded as a power series with respect to a quantity called the order parameter of the system. In the case of ferroelectric materials, the order parameter of the phase transition is the polarization P, for which the free energy is an even function of the small values of the polarization near the critical temperature of the phase transition. That is, the free energy F evaluated at the polarization P is equal to F evaluated at negative P. As a result, the expansion of the free energy F of the ferroelectric material near the Curie temperature have terms with even powers of P, and is given by the temperature-dependent value F naught of the free energy at zero polarization, plus a material constant alpha over 2, times the difference between the temperature T and the Curie temperature Tc, times the square of the magnitude of the polarization P, plus another material constant beta over 4, times the magnitude of the polarization P raised to the fourth power, and so on. This form of the expansion is the lowest order approximation of the free energy at its stationary point that is near the Curie temperature, since only the term quadratic in P has a temperature-dependent coefficient. In the standard expansion of free energy, all the coefficients are temperature-dependent and they have to be expanded with respect to the temperature. However, the leading term in such an expansion of the coefficient of the quadratic term must vanish at the stationary point, and the lowest order term in the expansion with respect to the temperature is proportional to the difference between the temperature T and the Curie temperature Tc. This is not the case for the coefficient of the quartic term, where the leading term of its expansion with respect to the temperature is a non-zero but dominant term for vanishing polarization. Then the dominant coefficients of the higher order terms can be approximated by constants. At the same time, for temperatures slightly higher than the Curie temperature, the equilibrium polarization is small, so the higher order terms can be neglected in the expansion with respect to the polarization. Consequently, the magnitude of the electric field strength E applied to the ferroelectric material given by the partial derivative of the free energy F with respect to the order parameter, that is the magnitude of the polarization P at a constant temperature T, is equal to alpha times the difference between T and Tc, times P. Then the magnitude of the polarization P can be written as the magnitude of the field strength E over the physical constant alpha times the difference between the temperatures T and Tc. However, the magnitude of the polarization P is also given by the vacuum permittivity epsilon naught times the electric susceptibility chi-E of the ferroelectric matter, times the magnitude of the field strength E. By comparing the two equations with each other, we can see that chi-E is equal to 1 over epsilon naught times alpha times the difference between the temperatures T and Tc. Then we conclude that the electric susceptibility chi-E of a ferroelectric material in a perielectric state is inversely proportional to the difference between the temperature of the material and the Curie temperature Tc, where the constant of proportionality C is the Curie constant defined by 1 over the vacuum permittivity epsilon naught times the constant alpha. This equation is called Curie-Weiss law, and it was introduced for ferromagnetic materials by Pierre-Weiss, a French physicist. It is an improved version of Curie's law stating that the magnetic susceptibility is inversely proportional to the temperature, and he derived this formula by determining the contribution of the magnetic dipoles having random orientations in ferromagnetic materials to the magnetization of these materials. In fact, he applied calculations based on statistical mechanics that are similar to those already presented here for determining the contribution of randomly oriented electric dipoles to the polarization of dielectrics. We note that this special class of polar dielectric materials are called ferroelectric purely by analogy to ferromagnetism. Despite the prefix ferro, which means iron, most of these materials do not contain iron at all. Like iron magnets that have a permanent magnetic field, these materials have a permanent, built-in electric polarization. In many crystals, electric polarization occurs when they are compressed or expanded in a specific direction and electric charges of opposite signs appear on the surface of the crystal. The phenomenon in which certain solid materials develop an electric polarization when they are mechanically deformed is called the direct piezoelectric effect. Piezoelectricity is the electric charge that accumulates in them as a response to mechanical stresses. Besides crystals, this effect has been observed in certain types of ceramics and biological matter like bone, for example human femur and weight-bearing bones. The typical examples for crystals and ceramics that can produce piezoelectricity are quartz, Rochelle salt, barium titanate, and sphalerite. Ionic crystals consisting of positive and negative ions arranged in a repeating, highly ordered three-dimensional lattice can have piezoelectric properties. If such a crystal lattice is deformed under the influence of external forces, then opposite charges will appear on the opposite faces of the crystal. The most controlled way to produce mechanical stresses in a crystal is a homogeneous or uniform deformation, where mechanical stress or strain is applied uniformly across the entire crystal structure. Under uniform stress, the electrical response depends entirely on the intrinsic symmetry of the crystal lattice. In the case of homogeneous deformation, the piezoelectric effect can be observed in crystals that has a lack of a center of inversion symmetry. The only exception is the cubic point group 432 of crystals, which is non-centrosymmetric but not piezoelectric due to its high rotational symmetry. If a crystal has a center of inversion symmetry, any internal charge separation caused by a uniform deformation is exactly cancelled by an equal and opposite charge separation elsewhere in the unit cell, and no net electric polarization is produced. Therefore, a lack of inversion symmetry is a strict requirement for a net macroscopic electric polarization to develop in a crystal. To observe the piezoelectric effect in quartz, we can perform a simple experiment. We already saw in the discussion on anisotropic dielectrics that alpha quartz crystals have one threefold axis in the z direction called c-axis or optical axis, and three equivalent twofold symmetry axes called a-axes or electrical axes, which are perpendicular to the c-axis. Between the three a-axes, other three symmetry axes called y-axes or mechanical axes of the crystal can also be defined. Here we depict one of the y-axes between the axes A2 and A3. In preparing the quartz crystal for the experiment, a thin plate is typically cut so that its faces are perpendicular to one of the crystallographic axes. In the figure we show a cut with the large faces normal to the A1 axis, that is in the plane spanned by the y-axis and the c-axis, where metal electrodes are deposited on the two large faces of the thin plate and crystal is connected to a high impedance electrometer. If the crystal is compressed along the A1 or the Y direction by applying some mechanical force, then a voltage pulse can be measured by the electrometer. The transient voltage generated in this effect is proportional to the duration and the rate of applied mechanical stress. Even under a constant, fixed mechanical load, the measured signal will not remain constant, as electric charges flows through the external circuit connected to the crystal and quickly leak away due to the surface contamination of the crystal or the ionization of the air surrounding the crystal. As a result, the voltage drops to zero. Switching from compressing to expanding the thin plate along the appropriate crystallographic direction, the polarity of the voltage pulse reverses. When the quartz crystal is compressed or expanded, its lattice deforms elastically, causing the centers of positive and negative charges in each unit cell to shift relative to one another because the crystal lacks inversion symmetry. This displacement induces a macroscopic polarization that causes equal and opposite bound charges to appear on the electrode-covered surfaces, creating a measurable voltage between the electrodes. A converse piezoelectric effect also exists where materials can undergo physical deformation when exposed to electric field. That is, an electric field applied to a crystal produces mechanical strain and the crystal changes its dimensions. The converse piezoelectric effect has some resemblance to electrostriction since both describe deformation of a material under an applied electric field. However, they differ fundamentally in their symmetry requirements, dependence on the electric field, and the materials in which they occur. The converse piezoelectric effect occurs when an applied electric field produces a mechanical deformation that is directly proportional in its magnitude and direction to the field strength. Because the strain changes sign when the electric field is reversed, the deformation depends on the polarity of the applied voltage, and this effect is possible only in crystals that lack a center of inversion symmetry. In contrast, electrostriction produces a strain that is proportional to the square of the electric field, which is the same for both positive and negative electric fields. The deformation is independent of the field polarity and occurs in the same direction regardless of the sign of the voltage. Consequently, electrostriction is a universal property of all dielectric materials, whereas the converse piezoelectric effect is restricted to non-centrosymmetric crystals whose symmetry permits a linear coupling between electric field and mechanical strain. In practice, piezoelectric materials intended for industrial or laboratory applications should possess several desirable properties. They should exhibit a large piezoelectric response generating a significant electrical signal from a given mechanical stress or a substantial mechanical deformation under an applied electric field. In addition, they should have high electrical resistivity to prevent the charges generated by the piezoelectric effect from leaking away. Finally, they should possess high mechanical strength and elasticity, as well as good thermal, chemical, and environmental stability to ensure reliable long-term performance. Examples for such materials are quartz, which is widely used for frequency standards and precision sensors, lead zirconate titanate, which is the most widely used industrial piezoelectric material, and lithium niobate, which is valued in high-frequency acoustic and the manufacturing of optical devices. One of the most typical applications of this effect is the piezoelectric pressure sensor or manometer designed to measure fast variations in pressure. When the pressure of a gas in a vessel acts on the diaphragm of the manometer, the diaphragm transmits a force to the crystal installed as a sensor, which is quartz or tourmaline crystal or a piezoelectric ceramic such as lead zirconate titanate. The applied force compresses the crystal, producing an electric polarization, and, as a result, equal and opposite charges appear on the electrode-covered faces of the crystal. Another area of applications of piezoelectric materials is modern electronics and radio communication. For example, piezoelectric transformers used in LCD monitor backlights or in AC adapters convert electrical energy at one voltage into electrical energy at another voltage using mechanical vibrations through the converse piezoelectric effect. Piezoelectric crystals or ceramics are also built in electronic oscillators, frequency filters, and ultrasonic transducers, where they act as a mechanical resonator with an extremely well-defined resonant frequency. Quartz filters provide extremely stable frequency selection because quartz has a very high mechanical quality factor, and crystal oscillators apply piezoelectric crystals to stabilize the frequency of an oscillator. Piezoelectric sensors are also used in automatics for vibration monitoring, dynamic force sensing, tactile sensing of robotic grippers, measuring rapid pressure fluctuations as seen in the first example, and so on. In acoustics, the piezoelectric effect is widely used for sound recording and playback in piezoelectric phonograph pickups, microphones, telephones, and hydrophones. Among the earliest and most important applications of piezoelectricity and are widely used in medicine, industry, and scientific research, we need to mention piezoelectric quartz ultrasound generators. These devices use the converse piezoelectric effect to convert high-frequency electrical oscillations into ultrasonic mechanical vibrations. When an alternating voltage is applied, the piezoelectric crystal expands and contracts periodically due to the converse piezoelectric effect. If the applied frequency matches one of the crystal's mechanical resonance frequencies, the vibration amplitude increases dramatically, producing intense ultrasonic waves. We finish the presentation on ferroelectricity and piezoelectricity with the discussion on pyroelectric effect and electrets. In certain piezoelectric crystals, the sublattices of positive and negative ions are displaced relative to one another in thermodynamic equilibrium, resulting in an electric polarization even in the absence of an external electric field. Piezoelectric crystals that exhibit such spontaneous polarization are called pyroelectric crystals. In other words, a pyroelectric crystal is a crystal that possesses a spontaneous electric polarization in thermodynamic equilibrium and whose polarization changes when its temperature changes. The spontaneous polarization is screened by surface charges and ions adsorbed from the surrounding air onto the crystal surface. However, when the crystal is heated or cooled, its spontaneous polarization changes, producing new surface charges that can be detected until they are compensated by charges from the surrounding environment. As a result, heating or cooling the crystal produces a temporary accumulation of electric charges on its surfaces, a phenomenon known as the pyroelectric effect. The pyroelectric current generated during a temperature change is proportional to the rate of change of temperature and materials properties of the crystal for a given electrode area. All pyroelectric crystals are piezoelectric because every polar crystal lacks inversion symmetry. However, the converse is not true. Most piezoelectric crystals are not pyroelectric because they do not possess a spontaneous polarization. Examples of pyroelectric materials include tourmaline, lithium tantalate, and many ferroelectric crystals such as barium titanate below its Curie temperature. Pyroelectric crystals are widely used in infrared detectors, where changes in the incident infrared radiation produce temperature variations that alter the crystal's spontaneous polarization, generating an electrical signal proportional to the radiation intensity. They are also applied in passive infrared motion sensors, where changes in the infrared radiation emitted by moving objects produce temperature variations in the crystal, generating electrical signals that indicate motion. Pyroelectric crystals are valuable in the manufacturing of thermal imaging devices as well, where they detect spatial variations in infrared radiation by converting temperature-induced changes in spontaneous polarization into electrical signals that form a thermal image. Another important application of pyroelectric crystals is in flame detectors, where they detect the characteristic fluctuations in the infrared radiation emitted by a flame and convert them into electrical signals for reliable fire detection. Pyroelectric crystals are also employed in laser energy meters, where the temperature rise produced by absorbed laser radiation is converted into an electrical signal proportional to the energy of the laser pulse. Besides the direct pyroelectric effect, pyroelectric crystals also exhibit the converse pyroelectric effect, whereby a change in the applied electric field results in a change in the crystal's temperature under adiabatic conditions. It is a thermodynamic phenomenon where a material experiences a change in temperature or entropy in response to an applied electric field. The converse pyroelectric effect, also known as the electrocaloric effect, is the exact thermodynamic reverse of the pyroelectric effect, and it can be shown that this effect is a necessary consequence of the direct pyroelectric effect and the laws of thermodynamics. The first law of thermodynamics tells us that an infinitesimal change in the internal energy U of a crystal is equal to the infinitesimal amount of heat delta Q exchanged between the crystal and its surroundings, plus the infinitesimal amount of work delta W done on the crystal by the electric field. By applying the second law, delta Q can be written as the entropy S of the crystal times the infinitesimal change dt in its temperature. We already saw that the infinitesimal work done on a dielectric material by an electric field is given by the magnitude of the electric field E times the infinitesimal change dP and the magnitude of the polarization field in the material. We also saw that Helmholtz free energy defines the thermodynamic stability of a system at constant volume and temperature, and it has a critical role in the interpretation of the behavior of ferroelectric materials. The Helmholtz free energy F of the pyroelectric crystal is defined by its internal energy U minus the product of its temperature T and entropy S. Then the differential of the free energy F is equal to du minus T times ds minus S times dt. If we substitute the expression obtained for the differential of the internal energy U into the right-hand side of this equation, dF can be written as E times dP minus S times dt. In experiments, one usually controls the electric field applied to the crystal rather than the polarization produced by the field. Therefore, we introduce another thermodynamic potential phi defined by the difference between the free energy F and the product of the electric field E and the polarization P. The differential of the potential phi is given by dF minus E times dP, minus P times dE. By inserting the expression obtained for dF into the right-hand side of this equation, d phi can be written as negative S times dt, minus P times dE. Since the differential of phi is expressed in the terms of the differentials of the temperature T and the magnitude of the electric field E, these quantities represent the two independent variables of the potential phi. Consequently, its differential can also be expressed by the sum of the partial derivative of phi with respect to T at constant E times dt, and the partial derivative of phi with respect to E at constant T times dE. By comparing the two equations derived for the differential of the potential phi, we can identify the entropy S of the crystal as the negative partial derivative of the potential phi with respect to the temperature T of the crystal at a constant field strength E applied to the crystal. Similarly, we can see that the magnitude of the polarization P of the crystal is equal to the negative partial derivative of the potential phi with respect to the magnitude of the field strength E at a constant temperature T. Then the partial derivative of the entropy S with respect to the magnitude of the field strength E is given by the negative second-order partial derivative of phi with respect to E and T. If we interchange the order of the partial differentiation, we can write the right-hand side as the partial derivative of the magnitude of the polarization P with respect to the temperature T at a constant field strength E. This result is a Maxwell relation between the entropy and the polarization of the pyroelectric crystal, where the partial derivative of the polarization P with respect to the temperature T at a constant field strength E in the right-hand side of the relation is defined as the pyroelectric coefficient P of the crystal. The later describes the pyroelectric effect in the crystal since P is the constant of proportionality for the pyroelectric current through a given electrode area generated by the change in the temperature of the crystal. For a non-zero pyroelectric coefficient, the Maxwell relation shows that an electric field applied to the crystal will change its entropy. Under adiabatic conditions where the differential of the entropy S vanishes, any variation in entropy must be compensated by a change in temperature. Consequently, modifying the electric field produces a temperature change, which is the converse pyroelectric effect. Dielectrics with permanent polarization is known as electrets by analogy with permanent magnets. In other words, an electret is a dielectric material that retains its electric charge or polarization after being subjected to a strong electric field. Electrets occur naturally in certain crystals, such as quartz, tourmaline and zinc oxide, but can also be produced artificially. We can produce an electret, for example, by cooling a molten mixture of wax and resin in the presence of an electric field. In this way, the molecular dipoles which become aligned with the applied electric field in the liquid state, are effectively frozen in place during solidification, allowing the material to retain its polarization even after the electric field is removed. An electret can retain its polarization for many years if it is protected by a suitable metal coating that prevents stray ions from the surrounding air from reaching the surface and neutralizing the surface charges. Electrets are widely used in electret microphones, electrostatic air filters, loudspeakers, radiation dosimeters, and energy harvesting devices because their permanent polarization provides a stable electric field without the need for an external power supply.